Hi everyone. Today we are going to cover the topic electrostatic potential and capacitance, NCERT Section 2.12 to 2.13 and Example 2.8. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So the topics that we are going to cover today is 2.12, the parallel plate capacitor, 2.13, effect of dielectric on capacitance, and example 2.8. In previous lecture, we have seen that what is capacitor and the principle of capacitor. Now we are going to discuss about a special type of capacitor. Capacitor can be of various types based on the shape of conductor. It can be cylindrical, spherical, or of any shape. But specifically, we are going to discuss about the parallel plate capacitor. Objective: derivation of formula of capacitance for a parallel plate capacitor. Okay, this is a diagram for parallel plate capacitor. So, as the name suggests, parallel plate. So, there are two parallel plates of conductors. One is at positive potential, one is at negative potential. Charge on one plate is plus Q, charge on second plate is minus Q. As we have discussed that there are two conductors involved in the capacitor. One is positively charged, one is negatively charged. There is a potential difference maintained between those conductors with the help of battery. Okay, so here the conductors are parallel plates. One is positively charged, one is negatively charged. And there is distance between them d, and A is the area of both these plates, which is same for both the plates, and sigma is the surface charge density for this positive plate, and minus sigma is negative charge density for this negative plate. And because charge on both the plates is equal, okay, charge on positive plate is plus Q and negative plate is minus Q. So densities are also same because area is also same for both the plates. So this is the electric field. This is electric field shown from positive to negative. So we know that from a plate or from a sheet, what is the electric field? As we have discussed in Gauss law, that there is a uniform electric field. Okay. So uniform electric field from the sheet and from the plate. So this is the electric field, which the value of electric field for a sheet is sigma by 2 epsilon naught. If it is thin sheet, if it is a plate of some thickness, then charges on both the surfaces are considered. So then electric field from this plate will become sigma by epsilon naught. So sigma here is surface charge density, which is Q upon A. Figure 2.25, the parallel plate capacitor. This is the construction of parallel plate capacitor. Parallel plate capacitor consists of two large plain parallel conducting plates with area A and separation D, where D is much smaller than the linear dimension. What it means that D, that separation between these two plates is very small as compared to the area. Means this D square, we have to compare it with area na, so we have to take D square. We can't compare a linear dimension with area. So okay, so we have to put the square. D square is much less than the area of this plates. So it means that separation, the amount of separation between the plates is very much smaller than the area of the plates. Why we are considering this? We will also get to know in the upcoming slides that why we are taking this assumption that d square is much less than the area of the plates. Okay, so with vacuum between plates, initially we will only take vacuum between the plates. There is no dielectric medium present between these plates. So there is vacuum between these plates. One plate has charge plus Q and surface density sigma equal to Q by A, while the other has minus Q and the surface charge density minus sigma. Derivation of formula of capacitance for a parallel plate capacitor. So we will derive the formula for capacitance of the parallel plate capacitor. So again, same diagram. Okay, in the outer region. Now here the thing is, this diagram is divided into three regions. This is first region, this is second region. This region beyond this first plate is first region. The region beyond this second plate is second region, and the region between these two plates is third region. So this diagram is divided into three regions. So in outer regions, that are first region and second region, above the plate 1 and below the plate 2, that are two outer regions, 1 and 2. What is the electric field, net electric field in these regions? That is above plate 1 and below plate 2. So electric field is 0. Net electric field outside these plates is 0. So why? So here we know that electric field from a sheet. What is this? Sigma by 2 epsilon naught. So from this positive plate, okay, the charges, that these positive charges are also present on this side also. Okay, so these positive charges are also present on this side, and negative charges also present on this side, because we are taking plate. So plate have charges on both sides. So what it will become? This positive, because of these positive charges. Okay, so electric field here is electric field in this second region is sigma by 2 epsilon naught due to these positive charges. Okay, so due to these negative charges, again electric field in this region is sigma by epsilon naught, but minus sigma by 2 epsilon naught. Due to these positive charges, this is the electric field direction in this region, which is sigma by 2 epsilon naught. Due to these negative charges, in this region, electric field is in this direction. Magnitude is again same, but in opposite direction, minus sigma by 2 epsilon naught. So both the electric field due to this positive and negative charges in this region will cancel out. Okay, so in second region it is 0. In first region also, due to these negative charges, electric field direction in this first area is this. And due to these positive charges, electric field direction in this area is in outward direction. So electric field, because of these two charge distribution, will cancel out in this region also. Okay, so it will become sigma by 2 epsilon naught minus sigma by 2 epsilon naught equal to 0. So in these two regions, first and second, net electric field is 0, as the field from both the plates cancel out. Between the plates. Now, what is scenario between the plates? Due to these positive charges, electric field is in this direction. Due to these negative charges, electric field is in also this direction. Okay, so these two electric field will sum up, add up, sigma by 2 epsilon naught plus sigma by 2 epsilon naught. What it will become? Sigma by epsilon naught. Sigma by 2 epsilon naught due to these positive charges, and sigma by 2 epsilon naught due to these negative charges. This will sum up because they are in same direction. So it will become sigma by epsilon naught. So what is sigma? Q by A. So what is electric field between the plates of the capacitor is Q by epsilon naught A, directed from positive to negative charges. This electric field is directed from positive to negative charges. Okay. This field is uniform except near the edges where fringing occurs but can be ignored when d square much less than. So what is this thing? So this assumption we have taken in the previous slide. So now I will explain why we are taking this and what is this fringing. Okay, so when this is the electric field between these plates, but at the edges for this region in the left side of these plates, the electric field will not be straight. Electric field lines will not be as straight as in the middle. They will be in the direction, they will be in this shape, like positive negative, like they are in positive negative, like they appear in the dipole, plus negative, plus and negative charge. They will appear as this shape. At these ends only also they will appear as this shape. So this is called fringing. At the ends of the plates of the plates of the capacitor, the electric field lines are not straight. They will be of this shape, like positive to negative, as we discussed the electric field lines for a dipole. Okay, so this thing is called fringing. So electric field is not uniform in this region. Electric field is only uniform between these plates, but near the ends it will distort and become non-uniform. But we have to consider uniform electric field because for our derivation we need uniform electric field between the plates. That's why we are taking this assumption d square is much less than a. This means the dimension that is specifying the separation between the plates of the capacitor is much less than the area of these parallel plates. This means these parallel plates are of very large area as compared to the distance between them. So this means that large amount of uniform field is present because the area of these plates is very large. So large amount of uniform field is present inside, but very small, due to this small separation, very small fringing is near the edges due to this small separation. So very small fringing can be neglected. That's why we are taking this assumption that this dimension, this separation will be very small as compared to the area. So area of this plates are considered much larger than its separation. This means there is large amount of uniform electric field inside the plates of the capacitor than the fringing effect. So non-uniform electric field will be very less. So it can be neglected. So this field is uniform except near the edges. So this field is uniform except edges where fringing occurs. This phenomenon occurs, but can be ignored when d square is much less than area. For uniform electric field, the potential difference V is equal to ED equal to QD upon epsilon naught A. So what is potential difference? We also know the relation between potential difference and electric field, which is electric field is equal to minus dV by dr. So for the time being we are taking only magnitude, not direction. So minus sign can be neglected. So E is equal to dV by dr. So what is the potential difference? V. Dr. What is the separation between them is D. So potential difference is equal to electric field into the separation between the capacitor plates. So what is electric field we calculated? Q by epsilon naught A into D. So this is a potential difference between the plates of capacitor. For uniform electric field, so that's why we are taking uniform electric field, and that's why we are taking that assumption to only take uniform electric field, because if there is non-uniform electric field, we have to integrate it, or this will make it very complex to find the final result. So as we are taking the assumption that there is very small separation between the plates as compared to the area, so we can neglect the fringing effect, which is very small as compared to the uniform electric field. So for uniform electric field, potential difference is given as this. Okay. So now, what is capacitance? We have studied in previous lecture, C is equal to Q by V, which is equal to, now what is the value of, so Q is Q, V is Q D upon epsilon naught A. So put the value of V here. So now we will get epsilon naught A upon D after solving. So this is the value of capacitance for a parallel plate capacitor with no dielectric medium inside. We took only vacuum inside. So without dielectric, capacitance of the capacitor is this, where A is the area of the plates and D is the separation between the parallel plates of the capacitor. Depends only on geometry. As we discussed that this C doesn't depend on Q or V. This C only depends on the geometry of the capacitor. And what is the geometry here is area of the plates and the separation between them. So it only depends on geometry. We can increase the area of the capacitor plates and capacitance will increase. We can increase the separation, capacitance will decrease. So to increase the capacitance, if we want to increase the capacitance, we have to increase area or we have to decrease the separation. So our assumption is true because we only want high capacitance. So we will take large area and small separation. So our assumption is true. For typical values of A, okay, now we will put the value, some values where is A, we will put A equal to 1 meter square and D equal to 1 mm. This is arbitrary values. We can put here A is equal to 1 meter square. Okay, and D equal to 1 millimeter. Then C will be equal to 8.85 into 10 to the power minus 9 farad. So now, have you seen a capacitor in your households or electronics with area 1 meter square? It is very large area as compared to electronic devices, electrical devices. So that much bigger capacitor doesn't exist or can exist with very large machines, within very large machines, electronic devices. But for our household, this 1 meter square is very, very large unit also. So D is 1 mm. This can be practical in households. For that thing also, large area and small d, capacitance is of the order of 10 to the power minus 9 farad, which is very, very small. As we discussed yesterday, that farad is very big unit. In this chapter, we will only take microfarad or nanofarad or picofarad. We will never take 1 farad. 1 farad is very large unit. So for 1 meter square of area of the plates and 1 mm separation, which is very small, 1 mm separation is very small and 1 meter square area is very large. Capacitance is still 10 to the power minus 9 farad, which is very small, showing that 1 farad is very large unit. It shows that 1 farad is very large unit. So we can't use 1 farad in practical applications. This is further demonstrated by calculating the plate area needed for C equal to 1 farad with D equal to 1 centimeter. And area, if we put C is 1 farad, C equal to 1 farad. If we take, that is not practical, but if we take 1 farad and the separation between the plates of the capacitor as 1 centimeter. So how large area, how much large area we should take to achieve this capacitance. So after putting 1 farad and d 1 centimeter, we will come to know 10 to the power 9 meter square. This is very large amount of area, 10 to the power 9 meter square, and requiring plates approximately 30 kilometer in length and breadth, which is not practically possible. 30 kilometer length and breadth. This large area we have to take of the parallel plates with their separation 1 centimeter, then will we achieve the capacitance of 1 farad, which is not practically possible. Okay. Now, to understand the effect of dielectric on capacitance, as we have discussed only the capacitance of dielectric, capacitance of capacitor with vacuum between its plates. Now we will consider the effect of dielectric. We have already studied the polarization in dielectric. What is the behavior of dielectric in the external field? Now, when we place this dielectric in the capacitor, due to the electric field present between the plates of the capacitor, this dielectric will behave accordingly. It will induce some electric field in the opposite direction and reduce the electric field within the dielectric. And now we will see how this phenomenon of the dielectric or properties of the dielectric going to change the capacitance of the capacitor. Okay. Dielectric modifies the capacitance of a parallel plate capacitor. So dielectric will modify. So it will increase or decrease, we will see. Initially, for a capacitor with plates area A separated by a distance d and charge plus minus q, charge density plus minus sigma, where sigma is equal to q by A. So in what was initially, we are given capacitor of plates of area A separated by distance d, charge on both the plates, one plate is plus q minus q, surface charge density on one plate is plus sigma minus sigma, where sigma is equal to q by A in vacuum. So in vacuum, what was the value of capacitance? So what was the value of electric field between the plates of the capacitor? Sigma by epsilon naught. Okay, as we have discussed. What was the potential difference? Why we are taking now E naught and V naught? This is the electric field or potential when there is a vacuum in between the plates. Now we will also see when there is dielectric material inserted between the plates. So V naught is equal to E naught into D. So what was the capacitance? C naught with vacuum. So C naught will be used as a capacitance of parallel plate capacitor with vacuum in its plates. So C naught is equal to Q by V naught, which is epsilon naught A by D. So what was this? This is the capacitance of capacitor with vacuum between its parallel plates. When a dielectric fully occupies the space between the plates, now we are inserting a dielectric medium which will fully occupies the space between the plates of the capacitor. So it gets polarized. Now we will place a dielectric medium which will exactly fits in between the plates of the capacitor. It gets polarized due to the electric field of capacitor. Okay, so it will not conduct the positive charges, charges from positive plate to negative plate. Because why? Because it is insulating material, non-conducting material. So it will get polarized due to the electric field between the plates of the capacitor, creating surface charge density sigma p and minus sigma p. As we have discussed that what surface charge density appear on the surface of dielectric? Sigma p. Surface charge density on the dielectric surface due to positive charges. Okay, and due to polarization. And minus sigma p is the negative surface charge density on the surface of dielectric due to polarization at the dielectric surfaces. Now, electric field in the dielectric becomes. So what is the electric field now? So dielectric, in dielectric medium, electric field is E naught. Without dielectric, in vacuum, E naught, which is equal to sigma by epsilon naught. Now there is an electric field due to these induced surface charge densities that is less in amount than this external field, which will be sigma p by epsilon naught. Okay, so what is the reduced amount of electric field? Sigma minus sigma p upon epsilon naught. Okay, so this will, so a reduced value of electric field will become sigma minus sigma p upon epsilon naught. Okay, so with potential difference, what will be the potential difference now? This E is the reduced value of electric field into D, the separation between the capacitor plates, equal to sigma minus sigma p D upon epsilon naught. Now we are taking full D because the electric medium is completely inserted between the plates of the capacitor. Now you have understood this. Okay, moving to the next slide. For linear dielectrics, sigma p is proportional to epsilon naught. So what are linear dielectrics? In which polarization is proportional to the external electric field. That we have done, that expression we have done in previous lecture. Polarization directly proportional to epsilon naught external electric field. And after removing proportionality sign, what constant appears? Chi E, susceptibility, electrical susceptibility. So that thing, that are linear dielectrics where this expression holds. Polarization is directly proportional to external electric field and the net dipole moment is in the direction of electric field. That are called linear dielectrics. So sigma p is proportional to E naught. So what amount of surface charge density will appear on the surface of the dielectric? It is proportional to the external electric field. Okay, so this thing leads to sigma minus sigma p equal to sigma by k. So how this thing comes? Because sigma p is proportional to E naught now. So why sigma minus sigma p upon sigma by k? So it is in the electric field chapter. You have also known that that epsilon naught. What is dielectric constant according to the electric fields? In electric field, you have also done the ratio of external electric field upon the reduced electric field equal to k. Or you may have done epsilon naught upon epsilon equal to k. Okay, so according to that thing, this sigma minus sigma p upon epsilon naught is equal to sigma by epsilon naught by k. Okay, so this is the reduced value of electric field, sigma minus sigma p upon epsilon naught. So this is external electric field, sigma by epsilon naught. What is k? We know that k is equal to E naught by E. So what is E naught? Sigma by epsilon naught. What is E reduced value? Sigma minus sigma p upon epsilon naught. So epsilon naught will cancel out. So sigma minus sigma p will go there and k will go there. After solving this equation came. Okay, where k is the dielectric constant. Okay, where k is the dielectric constant and k is greater than 1. Okay, so k equal to 1 for air. Okay, so k greater than 1 for any dielectric medium. So now what is V? V is equal to, what was V? At the place of sigma minus sigma p in previous equation, what was there? Sigma minus sigma p d upon epsilon naught. Now we will replace this sigma minus sigma p with sigma by k. So now the potential will become sigma d upon epsilon naught k, and this sigma is q by a. So what it will become? Q d upon a epsilon naught k. This is the value of potential here. Now what is this epsilon naught a upon D. Capacitance na? Now we will put this potential to find the capacitance. Capacitance with dielectric becomes C equal to Q by V. Put this value of V in this equation. It will become epsilon naught Ka by D. Now, this epsilon naught A by D, what is this? C naught, capacitance of the parallel plate capacitor with vacuum in its plates. Okay, so epsilon naught A upon D is the C naught, and this is K. So it will become K C naught. C will become K C naught. C is the capacitance with dielectric, and C naught is the capacitance without dielectric medium. So what is the relation between these two capacitances? Is capacitance with dielectric is equal to K times capacitance with no dielectric. Okay. To understand the relation and difference between epsilon naught, epsilon and K, product E epsilon naught K is called permittivity. That I have already discussed, that what is epsilon naught into K is permittivity of the medium. What is epsilon naught? Permittivity of free space, permittivity of vacuum or air, and this is permittivity of medium. So permittivity of medium is equal to permittivity of free space into dielectric constant, and dielectric constant is epsilon upon epsilon naught. Got it? Where Ka is equal to 1 for vacuum, and for vacuum epsilon is equal to epsilon naught. So for vacuum we use epsilon naught in the place of epsilon. For any other medium it is epsilon. For air or vacuum it is epsilon naught. The dielectric constant K equal to epsilon upon epsilon naught and also equals to C by C naught. As we have seen, C equal to K C naught. So what is K from there? C upon C naught. So what is the K? Again, another definition is there for dielectric constant. It is the ratio of capacitance with dielectric to the capacitance of parallel plate capacitor without dielectric. So again, another definition came. So it has many expressions. First, it can be shown in the form of permittivities. Dielectric constant is equal to the ratio of permittivity of medium to the permittivity of free space. Also, dielectric medium can be shown in the form of, in the ratio of electric field in the vacuum and electric field to the electric field in the medium. And now K can be shown as capacitance of parallel plate capacitor with dielectric to capacitance of parallel plate capacitor without dielectric, representing the factor by which capacitance increases from its vacuum value when a dielectric is inserted. Now we are sure because K is greater than 1, so C by C naught is greater than 1, which means capacitance with a dielectric is more than the capacitance without dielectric. And what is the conclusion? Representing the factor by which capacitance increases. So with the insertion of the dielectric between the plates of capacitor, dielectric increases from its vacuum value when a dielectric is inserted. Got it? The relationship holds true for any capacitor type, serving as a general definition of dielectric constant. So this relation K is equal to C by C naught, and the relation that dielectric constant and capacitance with dielectric increases holds for any capacitor type, for any shape or size of the capacitor conductors, whether it is spherical capacitor, whether it is cylindrical capacitor, whether it is of any shape. This relation and this conclusion holds for any capacitor type, serving as a general definition of dielectric constant. Now there is an example. Okay, example 2.8. A slab of material dielectric constant K has the same area as the plates of a parallel plate capacitor, but has a thickness 3/4D. Now, what is the twist? We have discussed the electric field. We have discussed that dielectric is completely inserted between the plates of the capacitor, and thickness of dielectric is equal to the separation between the plates. That we have discussed. Now, what is the question here? Thickness is not equal to the separation, but 3/4 times of the separation between the plates. Okay, now derivation can also be twisted by this thing. So you should know the concept. You can also derive for that thing, that if dielectric is not fully inserted, it has thickness less than the separation between the plates. So you can twist that derivation according to that. So now I will tell how you can twist the derivation, or how will you do the numerical if this type of thing appears. When D is the separation of the plates. Okay, how is the capacitance changed when the slab is inserted between the plates? Okay, so now we know that capacitance will increase. If there is a dielectric between the plates, the capacitance will increase. But how much? We cannot apply here C equal to K C naught. No, because that result is for complete insertion of the dielectric between the plates. It is not completely inserted. It is 3/4 of the separation. Its thickness is less than the separation. So E naught is equal to V naught by D. So electric field is equal to V naught by D, be the electric field between the plates when there is no dielectric medium. So this is for no dielectric medium case. So E naught is equal to V naught by D, be the electric field between the plates when there is no dielectric, and the potential difference is V naught. So this is the initial case. If dielectric is now inserted, the electric field in the dielectric will be E naught by K. This is the important line. Electric field in the dielectric will be E naught by K. Not in that place where dielectric is not present. Only inside the dielectric it is E naught by K. Okay, so this is the twisting point. How we will take a turn from the derivation. The potential difference then will be, now come to that point. E naught, now 3/4D is the thickness of the dielectric. Other 1/4D is without dielectric. There is vacuum only. Okay, so this E naught is present, this E naught when there is no medium, then this E naught is present in the 1/4D of separation. Means that separation, that place between the plates where there is no dielectric, this electric field presents. So this electric field into the separation where dielectric is not present. And E naught by K is the electric field, reduced value of electric field where there is a dielectric. In how much thickness is dielectric present? 3/4D. So potential is equal to E naught 1/4D plus E naught by K 3/4D. Now, take E naught D as common. 1/4 plus 3/4K. So after solving, V naught K plus 3/4K. So this is the potential difference now between the plates of capacitor. So the potential difference decreases by factor K plus 3/4K. So potential difference is decreased by this factor. Okay, while the free charges Q naught on the plates remain unchanged. Okay, while the free charges Q naught on the plates, charges on the plates is same. It will not change. Okay, so only potential difference is decreased. Why decreased? Because of reduction of electric field within the dielectric. So potential difference will also decrease. Does capacitance also increases? Because potential difference is increases. Capacitance is equal to Q by V. Q remains same. Q is not changing. The charges that are stored on the capacitor plates have to do nothing with the dielectric. So they will remain same. Okay, only V decreases. If V decreases, it means C increases. So C is equal to Q naught by V. So now decreased value of V is V naught K plus 3 upon 4K. So put this value in this equation. Now you will get C equal to 4K upon K plus 3 C naught. So this is the value of increased capacitance. Capacitance is increased whether dielectric is completely fitted inside the capacitor plates or of small thickness. If there is dielectric present of any thickness between the plates, capacitance will surely increase. But how much increase? It will depend on the thickness of the dielectric and nature of the dielectric. So capacitance will increase by the factor of 4K upon K plus 3, and C naught is the capacitance with no dielectric between the plates. Okay, so thank you. I hope you enjoyed the session.